Okay, so third variable t, yes. I'm going to put in quick parentheses or theta. Especially if you're using like sines and cosines, then theta might show up instead of t. Upon which x and y are both dependent. So t, the parameter, or theta, is my independent var. True? X and y are my dependent, which is weird. The when, not just the where. And more specifically, now we have I can show this. X is going to be its own function of time, and y is going to be its own function of time or function of theta, either way. Does anybody remember how parametric equations allow us to expand the type of motion that we can model? What type of motion were we doing in calculus last year, and how can parametric equations expand that? The dimensions, yeah. Because last year we were just doing straight up, straight down. Super awkward, like throwing a ball up and expecting it to hit you in the head. Like, Or straight left, straight right. There was no problem, unless I modeled it incorrectly, which sometimes for sake of illustration I kind of did. There was no problem where technically last year we were allowed to think about both to the right and up, to the left and down, to the left and up. We weren't able to think two-dimensionally on motion. It was only one-dimensionally, right, left, or up, down. That's it, rectilinear motion. But parametric says, oh, we can do two-dimensional motion, not just one. Which might beg the question in your mind, what about three-dimensional motion? Well, how about an x of t, y of t, and z of t? Don't worry, not this year. Although if you're bored, maybe pre-cal chapter 11 that we skipped last year, you might want to go peek at that. Three-dimensional vectors. Anyway. So we don't have to just stick with x of t or just stick with y of t. And when we do them both together, we have a plane curve. The AP might not always say, usually say plane curve. They could have used path last year for right, left. Minds a path a little bit. It's the two-dimensional instead of one-dimensional. So yes, it's called a plane curve, but we could also call it the path of motion. Are we good? If not, take a picture. I'm dual paging for just a second. Choop, choop, choop. So parametric equations, parts, points, specifics, initial point, terminal point. Where does it start? Where does it stop? Maybe it doesn't actually stop. Maybe it keeps going, but these are different terms that could come up in a problem. And hopefully, as you guys realized, at least every now and then last year, pictures can be helpful, or visualizing can be helpful. Not exactly you get points for the slope field where you just fill in. Remember, we're just doing the pre-cal coverage of it right now. We're expanding our summer review packet just a little bit. So initial point, easy. Translate the English. Initial point means what? And usually the starting point, usually, are when, or it's for t equal to 0. Now, t equal to 2 or t equal to starting point. Naturally be the ending point. Usually would turn. But I could say the initial point is maybe this is not my initial point could be some sort of, well, it's in physics, it might be initial and that's final. It's not a big deal, the notation. Just a warning, even though it's like, oh, it's a point, and it's a point, just remember, this is for some sort of given time, like x of a, y of a. They're not going to necessarily give you the x and y, they're going to give you the time. So even though it's usually for t equals 0, it doesn't have to be. So technically it could just be for some initial time a. So then you'd have to take the time, plug into the x, take the time, plug into the y to get the initial point, which is a little bit weird. Terminal point, same thing. That's going to have to come from some other time as well. How to sketch by hand. We mostly did horizontal tables last year, right? Just to make everything easy and able to fit a little bit better. Some of you might have done vertical tables, but we're going to have to do t's and x's and y's. And if they do give us some sort of like t is within some sort of a to b, then of course we would start at a, we would end at b. We would do a few representative ones in between just to get an idea. Yeah? But time, at least for our purposes, only moves one direction. So if time only moves one direction, we are going to plot these in a very particular order. Super important because time is only going one direction, and so to figure out the motion, we have things to watch out for. Man, we spent a lot of time on this in pre-cal. Let me do a quick little watch out. For the window, and specifically the T steps. The T steps could get kind of weird. You could do like a zoom standard to try to reorient it. I guess I could write out standard. The only problem is if you're like somehow someone borrows your calculator, they put you in degrees, it might totally mess up if your t step, which is like your theta step, is weird. Like if you have like a radian measure for a degree mode or a degree measure for a radian mode, stuff's going to get real weird real fast. You can do zoom standard to kind of fix that. You can also do zoom trig. That might be one that might reset it for you, just if something weird happens. And then be careful, you do have a T min and a T max. So depending on the curve, if you have too high of a range, it might look really weird, or if you have too low of a range, you might be missing part of it. Those are some things to think about. But that's like if something goes wrong, which, I don't know, maybe nothing will. So what's going on down here? The grapher can draw a curve only over a closed interval, so the portion it draws has endpoints even when the curve being graphed does not. You guys don't really realize this as much when you're in function mode. When you're in function mode, the grapher only graphs what fits on the screen. Show the infinite parabola, it only shows whatever fits on the screen. True? Okay. Over and over again, so you see the path. It's like an ellipse. You're like, sweet, it's an ellipse. And you could keep on going around, but you see the path. It's the ellipse. But maybe it's something where it's going up because parametric equations. It won't just be. You only had a certain time. You're like. feel like it's a pretty safe. Is it safe? If they don't give you a range, I'm pretty sure it's pretty safe to say that we could start at 0, pretty typically. Like, I love how from last year you would think of negatives and positives, and depending on the problem given, like they could do negatives. It's not very often though. I think I'm going to start with a positive. Sorry, going to the positive 0 in the forward direction. I guess you could do 1. Might have a little more fun with it. If you guys plug into x, that one's pretty easy because it just is what time is, right? Okay. With y, we have to plug into the function 1 minus t squared. So 1 minus 0 squared, 1 minus 2 squared, 1 minus 4 squared, 1 minus 6 squared. Okay, got a little awkward a little bit fast, but that's okay. When we go to graph our function, if we're saying that t equals 0 is our initial, you don't actually graph the times at all. You're just graphing what's going on during these times by graphing the x's and the y's. So we have 0, 1. We have 2, negative 3. We have 4, negative 15, and it'll keep on going from there. What does it seem to be? A downwards parabola, right? But how'd it go with us plugging it into our calculator? You guys rock it? Throwing in x1 is t, throwing in y1 is 1 minus t squared. If you wanted it to look the exact same as your by hand, you would need to go into window and t min, t max, the exact same range. Domain? Awkward. I'm going to use the general English term range just to say the beginning and the end. And you guys should get something pretty similar too, right? Now, you didn't have to do the exact same as me because you might have made a different range in your table. I didn't tell you what to do. I didn't tell you what times to use. But according to mine, going from 0 to 6.28, which is the same thing as 2 pi, I just stopped at 6. It's important to have your t steps if you are doing like a radian sort of measurement for t min, t max, which remember can be theta min, theta max. You're going to want little baby steps or else it's going to look super awkward. From how do we forget the t? The parameter. Something super decal that we figuring out the rectangular, aka equation with the exact same path. Thank you, ma'am. What's going on? Abby. I don't know. We're trying to go from y equals f of x. Now, as soon as you go to y equals f of x, like function mode, all of a sudden, which could be a function or maybe it's just an equation, because I said earlier, if you guys didn't catch it, parametric curves can definitely fail the vertical line. x is our normal independent. And so if we can get t alone in terms of x and then throw it into the y equation, all of a sudden y is a function of x, and we're back to what we're used to. Which in this one is super easy, because then you could say, oh, sweet, so y is equal to 1 minus x squared. So the path, awkward. The path is just a parabola that's been shifted up 1. But what does this not tell me that the page before did tell me? The direction, like I don't know if it's bouncing like from the left to the right or the right to the left. I don't know the direction of movement on the path of the particle or the car or the person or whatever. And what else don't I know? The time. So if I was looking specifically at something like, for instance, t greater than or equal to 0, it's not even over here, right? It's only over there. So not that the whole eliminating the parameter isn't useful. It's totally useful. It can at least give us some sort of idea as far as what the path looks like, but it can't tell us the orientation, the direction, and it can't tell us the when, the location at a particular time. So the where that goes with the when. It can only tell us, oh, this is the path, but we have no idea where the actual particle is at a particular time. But once again, super helpful for visualizing the path. So this is a super basic one. I'm hoping I have a better one on the next page, but I don't remember. I totally do, but we ran out of time, which totally makes sense because I have this being a 2-dayer, not a 1-dayer. Well, technically a 1.5-dayer. So tomorrow we need to talk about, can parametric equations get more exciting? But what could you start tonight, even though it's not due until Wednesday? Homework, but might you want your graphing calculator? Yes. Yeah. Not